Okay, welcome to my H6 homework assignment. This is the question we have today. We have a cylinder with a ring cross section. So it has an outer radius of 3 meters and an inner radius of 2. It has a length of 5 meters. It's centered on the z-axis and its bottom face is fixed. It has these two material properties that we're given. And the question asks to determine the moment on the beam at this top face and then determine the twist angle at the top face and then verify the twist angle and flex. So for part A, we need to find the moment at the top face. So to find the differential moment, we are going to cross the position vector r with the differential force, which is the differential force is just going to be the stress times the differential area. And so what we find is that the the differential moment is purely in the z direction, and it's going to be equal to this value here. Um, so what this tells us is that the moment is going to be, the stress applied is purely torsional because, um, so since the beam is centered on the z-axis and the moments that are being applied are only in the x and y direction, so that's going to make it so that there's only torsional uh, stress and no other types of stresses. Um, so once we have our differential moment here, we can go ahead and maple, and we're gonna basically integrate it over the area. And since we have a ring, the way I did it is I just first treated it as just like like a filled-in cylinder here, and I integrated it over as if the area was just a circle, and then I just subtracted out the moment caused by the smaller inner radius. And once I subtract them, then I have the total moment. And the moment we got was around like 400,000 Newton meters. And it's fairly large, but that's pretty much expected since the shear forces are acting in the same direction and they basically add up. So that's the moment for part A. So we answered that. And then for part B, we need to find the twist angle. Um, so we're basically just going to use Hooke's law of torsion over here. We're going to rearrange it for theta. We already have the moment from the past section, and then LZ is already given because the question says find the beam at the Z equals LZ face, so we know the value of that. We can find the torsion constant for a ring is going to be pi over 2 times the outer radius to the power of 4 minus the inner radius to the power of 4. And then we already know that the compliance matrix, no, sorry, we already know that the shear modulus is related to the Young's modulus by this equation. So we can just go ahead and plug that in, and we'll find the twist angle in maple. And so the result that we get is and it's in meters, and it's like zero. It's a 1.5 times 10 to the power of -5. And this is a fairly small angle, but it's pretty much expected since we have a high elastic modulus relative to the stresses that are applied on it. And also the beam is only 5 meters tall, and relative to its width, that's pretty short. So it shouldn't really be moving too much. If the beam was a lot taller, then of course we would have a higher twist angle, but we don't. So that's what's giving us our small twist angle. And for part C, we're going to now model it in Flex and try to find the twist angle. So to start off, we are going to find, well, first we have to create our shape in Flex, and I basically had to play around with it for a little bit. And I found that if I just make, in the region 1, if I just make two circles, uh, with R2 being the outer radius and R1 being the inner radius, that Flex basically just kind of connects them and it gives us the cross section that we need. And then we're just defining our variables here and our loads. And then now we can use the polar coordinate method to find the twist angle. So first well, it's kind of out of order, but y prime and x prime are defined as the original x plus the displacement, and then same thing with the y. So first thing we can do is that we need to find phi, and if the original twist is 0 for the before applying the stresses, we know that phi is just equal. We can use the a tan function to define phi, and then we can rearrange this first equation to find that, what theta is equal to, and then so we have everything we need here, and then we can set our magnification to 20,000, since we already know from our maple section that the displacement is already pretty small. Sorry, the twist angle is very small, so we won't be able to see it otherwise. Um, so this is what we get when we magnify it 20,000 times. It doesn't seem to be purely torsional because it's not uniform, the twist angle. There might have been an error in the way that we define the stresses, but I'm not 100% sure. It seems so it really only deforms in this purple section here, and that correlates with this area and that area. Sorry, this area and that area over there. Yep. And then, so the twist angle we get from flex is 1.9 times 10 to the negative 5, which is in the same order of magnitude as what we got in maple, but we calculated that it has like a 23% error, and it could be due if we just made an error in our code in flex. Um, Also, we already know that the way flex, when you apply when a shear when shear is applied in flex, that it doesn't rotate with the face that it's applied on, and when the angle of the force, and that changes the angle that the force is applied, and that can cause some error. And we also know that, well, we just fundamentally we derived the twist angle differently. In maple we used just Hooke's law, and then in flex we used the polar coordinate method. So that could have just given us just slightly different answers. And yeah, so that was pretty much it.